So Newton's second law is probably the most foundational law in classical mechanics. It states that the net force on an object is that object's mass multiplied by its acceleration. And we're going to look at just a few more examples of Newton's second law. We've done a few in class already, but just a few more examples to see how it works when we apply it to new situations. So there's this amusement park in ride called the rotor. How it works is it spins around really, really fast, so it gets going really quickly. And then the floor actually drops out, so those people inside this little like tube thing spins really quickly, and then they feel like they're stuck to the wall. They're not actually stuck to the wall though. What they're feeling is a friction force that holds them on, and it's a static friction force because they're not sliding, hopefully, if everything is working well. Of course they feel gravity down. If this ride is working well, then friction should completely balance out gravity. Those two forces should be equal. They feel one more force, and this last force is tricky. A lot of people think, oh, well, it should be out towards the wall, right? Because they're being thrown against the wall. There's actually no force pushing them against the wall. It's only their own inertia that makes them feel pushed against the wall, but there's no one in front of them, right? There could be nothing pushing on that person there. The only horizontal force they feel is actually from the wall, and the wall can't pull on you, that's impossible. Walls can only push, so the wall is pushing towards the center of the circle. So the third force they feel is a normal force from the wall pushing them in towards the center of the circle. And that force is the net force, right, because friction and gravity balance out. So that means the net force is towards the center of the circle. That means, of course, that the acceleration is towards the center of the circle. Because if Newton's second law says that the net force is equal to the mass times the acceleration, whatever direction the net force is in is the direction of the acceleration, because those are your two vectors in that equation. Alright, so the acceleration is towards the center, and it has a special name. It's called a centripetal acceleration. So in grade 12, you're going to learn a lot more about circular motion and centripetal acceleration. You'll learn some fun things like the fact that centripetal acceleration is related to your tangential velocity squared divided by the radius of the circle you're moving in. So that's actually kind of a fun relationship you'll dive into more in grade 12. We don't need that for grade 11 yet. And we're actually going to solve more of a grade 11 style problem that just happens to be moving in circular motion. Okay, so let's just write down our given information. What we know here is that centripetal acceleration, the acceleration towards the center of the circle, is 24.5 meters per second squared. And that's about all I'm really given here. My required, I'm looking for the minimum coefficient of static friction between the rider and the wall so that she doesn't slide down. So mu s is what I'm trying to find. This is actually a pretty good free body diagram here already, so I'll just use that. It just needs a coordinate system, so I'll make y positive up. And because the only force in x is actually this way, I'm going to make x positive this way. If you want to make x positive the other way, then you just have to make your normal force and the acceleration negative. That's fine, but I'll just make x positive in that direction, and it makes my life a little bit easier. Okay, so we've drawn our free body diagram. Next job will be to split anything that's in sort of components, like anything on an angle, but nothing is on an angle, so I don't need to make any components. I can dive into summing up my forces in x and summing up my forces in y. So, first in the x direction, the net force in the x direction is just that normal force, and it's going to be positive because it's backwards. And I've made x positive that way, so that'll work out to a positive value. The net force in the x direction is also the mass times the acceleration in that x direction, and the acceleration in that x direction is actually just the centripetal acceleration, right? That is the AC, centripetal acceleration right there. So I can say that MAC is equal to the net force in the x direction, which is just that normal force. Alright, so that's a start. I know acceleration, so this gives me a nice equation for normal force, so I'll just leave that over here. Now I'm going to sum up my forces in y. So in the y direction, there are two forces. There's the static friction force up and gravity down. We just write them in positively at first, right, just adding them together, but we'll put in the signs in our next step. So the static friction force is positive because up is positive, and it'll be actually at its maximum point. So you know how in general the static friction force, let's just do it in blue over here. In general, the static friction force is less than or equal to mu s Fn. if we're at the moment where we're looking for the minimum coefficient of static friction to like just barely hang on, then at that moment this becomes an equality. So we can actually use that FFS is equal to mu s Fn at this moment. So I'll put that in, mu s Fn, and it's going to be positive because the friction force is up. And my gravity force here is down, and the force of gravity is just negative mg. All right. If I knew a number, I could put that in, but it's actually nicer to do it with variables, and I don't know the mass, so it's good to go like that. In the y direction, the net force in the y direction will actually be 0, and that's because the acceleration in y is 0. So this person isn't moving at all up or down, so she's definitely not accelerating. So I can set this whole side equal to 0. So I have mu s Fn, that's my static friction force, negative mg, that's my gravity force, and that all adds up to 0. Right, so I'm looking for mu s. I don't know normal force, I don't know mass. It feels like I don't know anything here, but it's okay. I actually can replace the normal force with this part right here, right? Because I have this equation for normal force that I made over here. So I'm going to sneak that in and replace the normal force with that. So I get 0 is equal to mu s. And then instead of Fn, I can write in what Fn is, which is m ac. And then I still have the minus mg. And now I just need to rearrange for mu s. So we'll move the mg to the other side. And this is mac. And this is where it is so handy to be rearranging with variables instead of relying on calculating numbers as you go. We don't know the mass, but we don't need to know the mass of the person. I can divide both sides by m. And it turns out that the mass of the person actually doesn't matter here, so that's kind of cool. I get g is equal to mu s times ac, so I just need to divide both sides by ac to get rid of that acceleration there. So now acceleration is gone, and I get mu s on its own. So just write that out over here. Mu s is g divided by ac. Plugging in my numbers, that's 9.8 for g, and 24.5 for AC. So let's see what that is. We can make this 9.81 if we want to be like a little more precise there. Because we've got 3 sig figs on the bottom, that's kind of worth it. So I get mu s is 0.4, and it'll be 0, 0. I have to keep 3 sig figs for that. So I'll just lift that up a bit so you can see. Mu s is 0.400. That's my coefficient of friction there. Okay, next we're going to try a two-body free body diagram. So often it's pretty straightforward to see, well, what should I make my free body diagram about, right? Because there's usually just one object. But we can get into more interesting problems in physics. They'll have maybe 2 or 3 or many objects involved in them. And then you're going to need a few more free body diagrams. So let's say we've got this train. It's a toy train being pulled by a child. So the child's pulling here, applying a tension of 30 newtons. And we want to know, is the tension in these 2 ropes the same first? So will the 30 newtons here be 30 newtons here as well? And the answer is no. That's because the child has to accelerate. When the child pulls here, they have to accelerate the entire train. It's going to be harder to accelerate all of that mass than just to accelerate this little bit of mass here. This rope only has to pull the 8 kilograms, the smaller bit of mass. So the child has to work harder. They have to pull the whole train. So no, because FT1 has to accelerate the whole mass, the whole train, and FT2 just has to accelerate just the M2, just the one mass there, which is easier. Okay, so we're going to actually calculate what that FT2 is. To do it, we need more than one free body diagram. So when you have a system of multiple objects, a few good free body diagrams to draw are, first draw a free body diagram of the entire system altogether. So make the train and the car one object and look at all the forces external to that. What's nice about that is it makes forces like this tension force in the middle that I don't know, they disappear because they become internal forces, so you don't have to worry about them. That can be really useful for things like calculating the acceleration of the train. Once you know sort of the big picture, then it's good to zoom in and do free body diagrams of like either this car or the train engine, and look a little bit more closely. Sometimes both. Often you only need one. All right, so first we're going to start with our free body diagram of the whole system. So there's the car, Here's the engine. That's my engine. All right, not a great picture, but there it is. My first free body diagram I'm going to do in sort of pink here is of that entire system, so that we're making them one object. So what forces would the whole system feel? Well, it would feel force of gravity down. And that force of gravity is going to be, of course, negative. I'll make my coordinate system y positive up and x positive forward. It'll be negative, and it'll be negative the entire mass. So that's m1 plus m2, right? It's both the car and the train together. It's going to be 20 kilograms of mass here, times g, of course, so mg. The whole thing will feel a normal force, Fn. And the overall system will feel the force from the child, so that's Ft1, and that's the positive 30 newtons forward. It says that friction is negligible, so that means there won't be any friction force backwards on this system. Just makes life a bit easier. Okay, let's write down our given on the side here. I know Ft1, of course, is 30 newtons. I know M1 is 12 kilograms, that's the engine. I know M2 is 8 kilograms, that's the car, and that's it. The thing I'm required to find in the end is going to be Ft2. That's what I'm looking for in the end. But it's often a good idea to find the acceleration first. If you can get acceleration, that makes life a little bit better for you. So that's what we're going to start with. So using this free body diagram, I'm going to sum up my forces in the x direction first. So my net force in x, on this free body diagram, there's this tension force in the middle is gone, right? Because it's an internal force. It's not what acts on the whole train. It's just acting between the car and the engine, which is part of the train. The only x force is Ft1. So that's my only external force in the x direction. Now the net force in the x direction is going to be ma. Be super careful here. What do I put in for the m in this equation here? It's going to be the mass of whatever is in my free body diagram. So it has to be the entire mass, m1 plus m2. So when you're using F equals ma, be careful, the mass that goes in here is always the mass of whatever your free body diagram shows. So if my free body diagram is of the entire train, that is the mass of the entire train, m1 plus m2. All right. I can set these equal to each other, right? If net force is this and net force is that, those two things are equal to each other. So m1 plus m2 times ax is going to be equal to Ft1. And this is going to let me calculate ax, right? I can divide both sides by m1 plus m2. That cancels out. Divide by m1 plus m2 on this side. And I get ax on its own. So ax is going to be that tension force, 30 newtons, divided by m1 plus m2, that's the 8, plus the 12. And 30 divided by 20 is going to be 1.5. So acceleration in the x direction is 1.5 meters per second squared. Okay. So I am partway done here. So it's often a good idea, if you don't know acceleration yet, it's often a good idea to try and find acceleration if you can. Okay. This doesn't tell me the tension force though. In fact, there's no way this free body diagram can tell me the tension force. I need a new free body diagram for that. And there's actually two I could draw. I could either do a free body diagram of the car or of the engine. You can pick. I'll start with the free body diagram of the car. So this is the train car, the M2. So here's M2. It would feel gravity. In this case, the force of gravity is just negative m2g, right? It's just the mass of this guy. It would feel its own normal force, and it has the Ft2 is attached to it, pulling it forward, so it'll feel a tension force forward of Ft2. It doesn't feel Ft1 at all, because rope 1 is just attached to the engine, so the car wouldn't feel that at all. Put my coordinate system on there, of course, and I know a helpful fact, which is that this car is accelerating forward at 1.5 meters per second squared. So what's so handy about doing a free body diagram of the whole system is you can often find the acceleration of the whole system. And of course, this car is moving at the same rate as the train. They're all attached. It's like one fixed system. So this works really well when you have objects that are moving together at the same rate, same acceleration. Okay, so we've got our acceleration figured out. We're trying to solve for Ft2. It's probably a good idea to sum up our forces in x. In this case, the only force in the x direction is Ft2. So the net force in x is going to be m2 times ax, right? So the mass that I put in here is the mass of whatever my free body diagram's of, which is just m2. The acceleration is the acceleration of the whole system because the car and the train are moving, and the train engine are moving at the same rate. All right, so I could say m2 times ax is equal to ft2, and this lets me calculate ft2. So ft2 is going to be the mass of car 2, which is 8 kilograms, multiplied by the acceleration, 1.5, and that is 12. So I get 12 newtons, and it's forward pull in this case because that rope is pulling the car forward. If you want to check and just be sure physics isn't broken, you can always do another free body diagram of the train engine, and you could use that free body diagram to get ft2 and see if you get the same result. So here's my train engine. It's a really bad picture, but there it is. The train engine feels ft1, right? That rope is attached to the train engine. It also feels ft2, but it feels a backwards pull from that. So ft2 will be negative for the train engine. It feels its own gravity force, and it feels its own normal force. And it needs a coordinate system. Y is positive up, x is positive forward. So if I sum up x direction forces on the train engine, I would have ft1 and ft2. I have both of them. The net force in the x direction on the train engine is going to be the mass of the train engine. The train engine is m1, the 12 kilogram mass, times the acceleration of the engine, which is also the acceleration of the whole system. So I know m1 ax is going to equal ft1 plus ft2. I'm trying to solve for ft2, so I'm going to move ft1 to the other side. So I have m1 ax minus ft1 gives me ft2. And then I'll plug in all my numbers. So ft2 is going to be m1, which is the 12 kilograms, times ax, the 1.5, minus ft1, which is the 30 newtons. And that gives me, so 12 times 1.5 minus 30 is equal to negative 12 newtons, which is awesome because that is exactly the same value as the ft2 I got here. Right, this is a forwards tension, and this one is a backwards tension, so negative 12, but it's exactly the same tension. So physics works, which feels really good. So this problem is a little bit beyond the level of our course. This one comes from first year engineering, but I wanted to show to you, that actually you maybe are closer to doing first year university problems than you think. You've solved a lot of hard problems already in grade 11, and you might find that you can actually do this. So yeah, so feel free to listen along and try out some of the extra challenge problems that are in your package too. Alright, so here you have a situation that is actually surprisingly a lot like the rotor. It just doesn't look like it right away. So you have a big box like this, M1, that's an 18 kilogram box. You're applying a force to it, an applied force, that's quite large, and this whole system is accelerating really quickly in this direction. Because it's accelerating so fast in this direction, M2, which is actually only held up by, of course gravity wants to pull it down, it's only held up by a static friction force. M2 will actually stay stuck to the side as long as you keep accelerating fast enough. What we're going to do is try and figure out what force you have to apply in order to keep M2 from sliding down. So we can do a few free body diagrams here. It's going to be a really good idea to do a free body diagram of the whole system, so of the two boxes together. So that's going to be one of them. It's also going to be a good idea to do a free body diagram of just M2. And if you wanted, you could also do a free body diagram of M1. Turns out you don't need that, but if that makes you feel better, feel free to draw one of those too. I'm going to start with my free body diagram of M2. So just because it's a simpler free body diagram and there's not too much on it, so I might be able to solve for a few things. That's kind of why I'm hopeful there. So M2 is going to feel its own force of gravity pulling it down, Fg. It'll feel a friction force, right, from M1. It wants to slide down, so that friction force is what holds it up. So there's a static friction force, hopefully static, right, because it's not sliding, that's the idea. M1 is also pushing on it, so there's a normal force here. So there's a normal force coming from M1, like that. So this is actually a lot like the rotor problem, right? You can kind of see like that person spinning around in the amusement park ride felt a friction force up, gravity down, and a normal force towards the center of the circle in that case. In this case, we're not moving in a circle, we're actually just moving in a straight line, but we still feel this big normal force, which causes a friction force, which keeps the block from falling down. So that's kind of the similarity. We can't forget our coordinate system, of course. Y is positive up, we'll make x positive forward. And then once we've got our free body diagram drawn, it's always a good idea just to sum up our forces in x and sum up our forces in y and kind of see what we get. So we'll start with x. The net force in x is just Fn. That's the only force in the x direction. And, oh, sorry, that's an x, not a y. Sorry about that. X. The net force in x is also the mass, and it's m2 times the acceleration. So the mass that goes in here is just the mass of whatever my free body diagram is of. My free body diagram was of m2, so m2 has to show up in there. Okay, so m2 times ax is going to equal then just the normal force. All right, this seems nice, but I don't know the normal force and I don't know ax. I do know m2, but I'll just stop there. Oh, I should write down my given over here so we can know what we know here, right? So given, I know m1 is 18 kilograms. I know m2 is 2 kilograms. And I know the coefficients of friction. So I know mu k is 0.6 and I know mu s is 0.8. All right. And what I'm required to find is Fa eventually. But often it's a good idea, if I can find this acceleration, that will go a long ways. So sort of my other thing I'm going to try and find is the acceleration. All right. In the y direction, the net force in the y direction is going to be, well, there's a friction force here, FFS, and there's gravity, FG. In the y direction, the net force in the y direction will be 0, and that's because that block is not moving at all in the y direction, so there's no acceleration up or down at all. So I can say 0 is equal to my friction force plus my gravity force, and then let's start filling in what these are. So at the moment where m2 is just about to slip down, right, we're looking for the minimum force of Fa to prevent m2 from slipping. So that means the moment when that block is just about to slide. So at that moment, that inequality of static friction forces less than or equal to mu s Fn becomes an equality. So it'll become just equal to mu s Fn. And the force of gravity on m2 is just the mass of m2 times g, and it's negative because my coordinate system shows up as positive. So negative m2g. This looks actually really hopeful. I have an equation that involves acceleration here, but also the normal force. I have an equation that doesn't involve acceleration, but does involve the normal force. So maybe if I rearrange this for the normal force, I could kind of sneak it in here and then solve for acceleration, or vice versa. I could take all of this and sneak it in here. You can go either way. I think your easiest bet, it's kind of 50-50. I think your easiest bet is going to be to sneak this one, take that, and replace Fn right here. Just because it's already nicely rearranged for Fn, it just seems like it's a good idea. So I'll have 0 is mu s times Fn, but I know Fn is m2 times ax, and then minus the m2g here. We can move the m2g to the other side, so it's positive. So I get m2g is equal to mu s m2 ax. Then I'm going to divide both sides by m2. That's kind of nice because it cancels out the mass here. I also want to get ax on its own, so I'm going to divide both sides by mu s as well. And I get ax on its own. It's just going to be g over mu s. And let's get a number for that, just to make our lives easier. 9.8 divided by 0. Mu s is 0.8. Sorry, 0.8. Okay, so 9.8 divided by 0.8 is 12.25 meters per second squared. All right. We could even make that a little bit more precise if we want. We could do 9.81 divided by 0.8. It doesn't really matter. I'm good with either. A little more precise would be 12.2625 there. If I do 9.81, make it a little bit better. All right. So that was handy because that little free body diagram of M2 gave me the acceleration of the system, and I know these two blocks are moving together. So if I know the acceleration of M2, that's the acceleration of M1 as well. So that's going to be really useful. Now we're going to zoom out and do the free body diagram of the whole system all together on a new page though. So I have M1 is here, and I have my little M2 attached to it here. And I'm going to look at all the forces that are on that entire system altogether. So I draw a box on it just so I know what my system is. All right, there's the applied force that you apply to M1, right? So that is actually the force we want to solve for. The whole system would feel a force of gravity. This is going to be the mass of the entire system times g. It'll also feel a normal force. And there's a friction force here, right? Because M1 is sliding on a surface. So there's an F, it's a sliding friction force, FFK, because that guy's sliding. The static friction force and the normal force and all the forces in between M1 and M2 here, we don't have to draw those anymore because those are internal forces now. That's between M1 and M2. It's not some external thing pushing on our whole system. So that makes our life a little bit simpler. And we need a coordinate system. Y is positive this way, X is positive this way. I know the whole system's accelerating this way, and I even know what that acceleration is, so that's kind of nice. Okay, let's start by summing up our forces then, same way we always do. So let's do X first. So the net force in X is going to be that applied force that I'm looking for, plus the friction force. I know that the net force in X is going to equal the mass times the acceleration in the x direction. The mass that has to go in here is the mass of the entire system, the mass of everything in my free body diagram, right? So that's going to be M1 plus M2. So that means that M1 plus M2 all times the acceleration that I've already found is equal to FA plus FFK. Do one more simplification here before we move over to the y side. Alright, we don't know FA, but we do know that FFK is going to be negative, it's backwards, and it's going to be mu k times Fn. There's no weird inequality with kinetic friction, it's just always equal to mu k Fn. Seems like we probably need the normal force, right? We know acceleration, we know everything else in this problem except for FA and the normal force. So we're going to need summing up our forces in the y direction to get the normal force. So I'll do that over here. So in the y direction, I have the force of gravity, and I have the normal force. I also know that in the y direction, the net force is 0 because it's not accelerating in y. So I can say 0 is equal to the force of gravity plus the normal force, and then I'll fill in what these are. So the force of gravity is negative because gravity's down, and it's the mass of the entire system, M1 plus M2 times g, and then there's the normal force over here. All right, let's move all of this negative stuff to the other side, and it'll become positive, and then I'm going to write it forwards just to make it look nicer. So I get Fn is positive M1 plus M2 times g. All right, I can take all of this now, this nice equation for Fn that I have here, and sneak it in for Fn right there, right? And that replaces my Fn over here. So I'll rewrite this equation out. M1 plus M2 times AX is equal to FA minus mu k, except for instead of Fn, I get to write what Fn is, which is this stuff here, M1 plus M2 times G. And this is awesome. We now know everything except for FA. Let's just move all of this stuff to the other side. So I get M1 plus M2 times AX, and then this is all subtracted, so it becomes positive over here, plus our mu k M1 plus M2 times G, and that all equals FA. We have found our force. We just need to plug in our numbers now. So FA is going to be M1 plus M2, that's 20 kilograms. M1 was 18, that was 2 kilograms, so adding together we just get 20 there. Times our acceleration we found was 12.2625, plus mu k is 0.6. M1 plus M2, that's 20 again, and G is 9.8. And that gives me FA. So now I just toss that all into my calculator. 20 times 12.2625 plus 0.6 times 20 times 9.8, and I get 362.85. With significant figures, it looks like I have 3 sig figs is my smallest number of sig figs, so I can report this just to 363. So Fa is 363 newtons in order to keep M2 from sliding down. And that's it.